Now see students, till now we have studied one dimensional steady state heat conduction without heat generation. Now we are going to study one dimensional steady state heat conduction with heat generation. Fine. So now first of all we must understand heat generation. I have already explained, again repeating. Now see, suppose this is a body or this is our system and there passes a wire and through wire we are flowing current I and the resistance is R. So some heat will be developed that is equal to I square RT, where this T is time. Fine. So what we are doing here is electrical energy is getting converted into heat energy, and we know that electrical energy is high grade form of energy, whereas this heat is nothing but low grade form of energy. Fine. Now what all we can say is that there might be some nuclear reaction in the system. So this nuclear reaction, in this nuclear reaction, what is happening? Nuclear energy is getting converted into heat. Fine. Similarly, in a chemical reaction, your chemical energy is getting converted into heat. Fine. Or what we can say is that suppose there is a shaft work and this shaft is rotating within the bearings. Fine. So there will be some frictional heat losses. Now see, suppose this is the shaft. Now it will have bearings on its surface so that it can easily rotate. Fine. And between, when there is a contact between the surface and the bearings, some of the energy is lost in order to overcome the friction. So frictional losses are nothing but your heat losses. Again, this is your high grade form of energy and this is your low grade form of energy. So in all these process, what we are seeing is that high grade energy is getting converted into low grade energy, and this is nothing but heat, and such a phenomena is known as your heat generation. Such a phenomena is known as your heat generation. Fine. So we can say that heat generation is a phenomena of conversion of high grade form of energy into heat within the conducting material. Fine. Fine. And what we consider here is that there is uniform heat generation. See, what do we mean by uniform heat generation? Suppose this is a heat conducting material. Fine. When we say uniform heat generation, that means heat is being generated uniformly throughout the volume of this material. Fine. So, heat is uniformly generating throughout the volume of this material. And when we see that there is uniform heat generation, the temperature at any point on this surface remains constant. See, take any point on the surface, the temperature will be Ts. The temperature will be Ts. That means uniform heat generation means uniform surface temperature. Fine. It means uniform surface temperature. Now see, when there is uniform surface temperature, what we can assume is that the maximum temperature is at the center. See, suppose this is a body. Now, everywhere the temperature is Ts. The surface temperature is constant. And some heat is being generated within the system. That means some heat from the center is going to the surface, and ultimately you have ambient conditions T infinity such that we assume surface temperature is greater than T infinity. So, some heat will be generated here, Q dot generation, and this generated heat will be conducted, Q conduction, and this conduction takes place till the surface, and beyond this surface there will be Q convection. And for steady state, or for equilibrium condition, we know that your Q generation will be equal to Q conduction will be equal to Q convection. Fine. And moreover, when the temperature is uniform at the surface, what we can say is that here the temperature will be T maximum, and it is generally denoted by T naught. So, here the maximum temperature is always at the center. Fine. Now, consider the case of slab. Suppose this is the slab. Fine. Now see, some heat is being generated within the slab, so it will have uniform surface temperature Ts on both the sides, and the maximum temperature will lie in the mid plane. See, this is the this represents your mid plane. So here at mid plane the temperature are maximum, or it is represented by T naught. Fine. So here the variation is something like this. Here the maximum temperature T naught at the mid plane, and here the surface temperature Ts, which are uniform. And we see that the maximum temperature always occurs at the center, and the center becomes the mid plane in case of a rectangular slab, and this is only possible in case of uniform heat generation. Fine. So come to the case of cylinder. Fine. Now see, suppose this is the cylinder, let this be the cylinder. Fine. Now some heat generation is taking place in the cylinder, so the center will become its center line. Fine. And at center line the temperature will be T maximum, which is represented by T naught. Fine. And in case of sphere, this is our sphere, and the center point will be this one. So here we obtain a center point, and at this center point we obtain maximum temperature represented by T naught. So here the maximum temperature in case of slab occurs at the mid plane. In case of cylinders, the maximum temperature occurs at the center line, and in case of sphere the maximum temperature occurs at the center point. Fine. Now first of all we will see rectangular coordinates. Fine. This is the rectangular slab and this is the mid plane. Fine. If we see in the front view. Fine. Now see, here we have obtained T naught, and here is the temperature Ts, and here the surface temperature again Ts, and the temperature variation is something like this. Fine. And in case of rectangular slab, at the mid plane we assume x is equals to 0. Fine. And when we go in this direction we take x is equals to minus L, and when we go in this direction we take at this point x is equals to length L. So the thickness of the slab can be taken as 2L. Fine. Now what we say is that your Q generation, the amount of heat generated in this rectangular slab, will ultimately be lost to its surrounding. So this Q generation, here is your Q generation, and this heat will propagate by means of conduction to the surface, and beyond the surface it will be lost by means of convection. And in equilibrium state, for equilibrium state, this amount of heat generation should be equal to your Q convection, and let the ambient air temperature be T infinity. This Q generation can be written as Q dot into volume, where this Q generation, the units are your kilowatt per meter cube. This represents the amount of heat generated in 1 meter cube of the volume, and let the total volume be V. So, total heat generated will be Q dot into V, fine, and this will be equal to your H into surface area. Now see, the slab will have this area which is responsible for heat losses by convection. Similarly, you have one area parallel to it. So, the total surface area will become 2A, where this is nothing but area A. This is nothing but area A. And what is the temperature difference? Ts minus T infinity. This is the temperature Ts at the surface and ambient air temperature as T infinity. Fine. So, from this we can write your Ts minus T infinity comes out to be your Q dot into V upon H into 2A, and this volume for rectangular slab will become equal to area into this thickness. Here the thickness is 2L. So, the volume becomes area into 2L. Fine. So, this equation can be written as Q dot into area into 2L upon H into 2A. So, this equation becomes Q dot L upon H. Q dot L upon H. So, Ts minus T infinity is this, and it is applicable for uniform heat generation in a rectangular slab. In a rectangular slab. This is very important. This relation gives us, relation between your surface temperature Ts, surface temperature Ts and ambient temperature T infinity. Fine. So, this relation is useful to find the relationship between surface temperature and ambient air temperature. Fine. Now, see students, this term volume upon surface area. See, here this is nothing but your volume and this is nothing but your surface area responsible for heat convection. Fine. So, this term is nothing but your characteristic dimension LC. Characteristic dimension represented by L and C in subscript. Fine. Now, come to cylindrical coordinates. Suppose This is a cylinder, fine. It has radial distance r, the radius is r and the length is L, fine. So see, this area is nothing but area equal to pi r square, fine. So the volume V becomes equals to pi r square into length L, and what will be the surface area? The surface area, this one and this one. So suppose this is the cylinder, so this area is your surface area. So the surface area responsible for heat convection becomes 2 pi r L. So the characteristic dimension here becomes fine. So it is nothing but your r by 2, fine. So here the formula Ts minus T infinity is nothing but Q dot by H into R by 2, fine. Now come to spherical coordinates, fine. Let this be the sphere and this is the center point and the radius is r. So here the surface temperature is Ts, the ambient air temperature is T infinity, fine. So your volume will become equal to 4 by 3 pi r cube, fine, and the surface area becomes 4 pi r square. So what will be the characteristic dimension? 4 by 3 pi r cube upon 4 pi r square. So the characteristic dimension comes out to be r by 3, and this relation can be written as Ts minus T infinity is equals to Q dot upon H into R by 3, fine. Clear hai? Now we need to summarize what we have studied. Now first of all we have studied uniform heat generation. Uniform heat generation means uniform surface temperature and T is equals to T max at center, fine. Now the first case was that of rectangular slab, fine. The second case was that of cylinder, and the third case was that of sphere, fine. In case of rectangular slab, this is the mid plane, where the temperature is T maximum. Fine, and let this be your T naught or T maximum. This is also represented by T naught, and this is the surface temperature Ts, and this is the surface temperature Ts. So the relation Ts minus T infinity, where T infinity is the ambient air temperature. Fine, it is nothing but your Q dot into characteristic dimension upon H. Fine, and this characteristic dimension here is nothing but your length L, where this is the length L, and again this portion is length L. So L is nothing but half the thickness of slab, half the thickness of slab, because this 2L becomes your total thickness. Fine, and this point here we assume x is equals to 0 at this point. Fine. Now for cylinder, this is our center line, and at this center line T is equals to T max, and it is represented by T naught. Fine. And the relation between surface temperature Ts and ambient air temperature is Ts minus T infinity is equals to Q dot into characteristic dimension Lc upon H, where Lc is R by 2, and this is your radius of the cylinder R. Fine. And in case of sphere, this is our center point where temperature is equals to T maximum, and it is also represented by T naught. Fine. Let the surface temperature be Ts and the ambient air temperature be T infinity. So the relation is equals to Q dot into characteristic dimension upon H, and here the characteristic dimension is R by 3, where R is nothing but your radial distance, the radius of sphere R. Fine.